All right, welcome back. Apologize, I did not make a video yesterday. The best way to do this is to do it every day for a significant length of time each day. Um, okay, so I'm on to the guided exercises. So I'll be using ChatGPT for this. So, and I'll be using ChatGPT 4. So I'll try to get through all of them, but if I run out of inquiries, I might need to end it earlier. All right, so this is the plan. Act as my LPIC-1 tutor. Use the Socratic method to teach me the answer to this question. And I will read the question out loud before I hit enter. The question is, on a machine equipped with BIOS firmware, where is the bootstrap binary located? And I already know the answer to this. It's in the first 440 bytes of the storage disk that is specified. I mean, any storage disk has it pretty much, as far as I understand, but it's located like where it's going to be used is the one that's configured in the BIOS in the startup options, and it's the first 440 bytes, and it's called the master boot record. I think I'm not sure if that's just automatically burned into every disk as a, or if you have to format the disk first and create that. Um, Let me look at my uh, disk partition on this. Okay, so here's information about. Okay, so yeah, we can see now. My system actually uses uh, UEFI, which is kind of surprising because it's not like a Raspberry Pi or a tablet or something like that. It's a gaming tower PC, and you can still see it still uses UEFI. So the EFI system partition, that's in um, that's on a. Is it a mechanical or is it? No, I don't think I have any mechanical drives on here. It's on the solid state. But yeah, here's the first part. Here's the um, disk file system is NTFS, and then here's the EFI system partition. But on a BIOS system, you'd have something like this. But instead of it being an EFI system partition, it would be the master boot record, and it would be 440 megabytes instead of 100.
Absolutely, let's use the Socratic method to guide you to the answer. Firstly, let's consider, what is the purpose of a bootstrap binary in a computer system?
Oh, so this is the bootstrap binary. Maybe that's different from the. So the purpose of the bootstrap binary. Maybe that's different from the boot partition. Is to hand over the boot up process to a firmware such as grub that is used to initialize the start of the OS which may include selecting between operating systems if multiple are installed.
That's correct. The bootstrap binary is a crucial piece of software that kicks off the boot process and loads the operating system. Now, let's discuss where it's stored. If we're talking about a system with BIOS firmware, the bootstrap code is typically stored somewhere permanent and non-volatile. What type of memory fits these characteristics on a computer system?
Okay, so since we're talking about a system with BIOS firmware, uh, permanent and non-viable, so in a storage disk, such as a mechanical or solid hard drive.
Yes, you're right that hard drives can store non-volatile data, including the operating system and other essential files. However, the BIOS needs to access the bootstrap binary even before it can read from these types of drives. So, keeping this in mind, is there any other type of memory that is non-volatile but can be accessed immediately when the computer powers on?
Yes, on the board there is read-only memory.
Absolutely correct. This read-only memory on the motherboard, commonly known as ROM, is the place where the BIOS is stored.
Yes.
Now, given this, do you think you can answer the original question about where the bootstrap binary is located in a BIOS-equipped machine?
Oh, is that the case?
Precisely. The bootstrap binary is indeed located in the ROM on the motherboard. In the context of a BIOS firmware, the BIOS bootstrap program, also called BIOS ROM or the BIOS itself, is stored in a ROM chip on the motherboard. When the computer is powered on, the CPU accesses this BIOS ROM and starts executing the bootstrap code it finds there. This code in turn is responsible for initializing various hardware devices on the motherboard, running power on self-test, post procedures, and eventually loading the bootloader from the bootable storage device, like a hard drive or SSD, which then loads the operating system. Well done on reaching the conclusion through the Socratic method.
All right. Is that? Oh yeah, the master boot record and the bootstrap binary are different. Oh no, wait, what? Okay, so ChatGPT 4 is obviously limited. It makes up and hallucinates things. So like it can't be trusted. And it looks like it got this one wrong. I was right when I said that it was in the it's not in the wrong no. 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 Bad ChatGPT 4. Bad ChatGPT. You got this all wrong. Tell me how this was wrong and tell me correct information. Tell me where and why what you said was wrong and tell me what is correct instead. Think out loud.
Apologies if there was some confusion earlier. Let's revisit our topic. The initial response to the question on a machine equipped with a BIOS firmware, where's the bootstrap binary located, wasn't entirely correct. Here's why. In the context of a BIOS firmware, the BIOS itself is a form of bootstrap code and is stored in ROM, but it's important to make a distinction between the BIOS and the bootloader, which is the next step in the boot process. The BIOS does initiate the boot process, as mentioned earlier, but the bootloader, Grub for instance, or Windows Boot Manager, is stored on a bootable device, usually the hard drive. The BIOS initializes the hardware and then goes through a process called the boot sequence. It checks for bootable devices, according to the order specified in the BIOS settings. The first bootable device it encounters will be used to continue the boot process. This device contains a small program in its first sector, also known as the master boot record or MBR, in case of BIOS, MBR setup, or in an EFI system partition, in case of a UEFI, GPT setup. This program is the actual bootstrap binary or bootloader, such as Grub, Lilo, or Windows Boot Manager. So, to correct the previous statement, in a BIOS MBR setup, the bootstrap binary bootloader is located in the master boot record (MBR) of the bootable device, typically a hard drive or SSD. I apologize for the confusion and I appreciate your patience in seeking the correct information.
All right, I'm gonna. Uh, uh, what do I like? What? It's accurate as far as I know. As I know, the prior information given in this thread was totally incorrect, saying that the ROM on the motherboard. Now, what is in the actual ROM on the motherboard? I forget. Oh, which contains the BIOS. Only the BIOS UEI configuration utility also contains boot up software such as Grub, loader. Incorrect. This information is on a formatted and partitioned storage disk. There we go. Okay. So this is what I mean. It's like ChatGPT can lead you astray. It can say, BS crazy things that are wrong, but, it's usually not, it's like, it's still useful, I think, in my opinion. Like, and if you're trying to learn something and really be an expert in it, hearing wrong, and disinformation, your knowledge set and your experience should be more robust than to just go along with like what you hear and then kind of smile and nod. You should be able to call it out and say that is wrong in a nice way. Not it, you shouldn't be a total a hole everywhere you go, but if things aren't working because nobody knows what they're doing, you as the expert should be able to fix it. Okay, so we got the answer to this. It's located on the um, formatted and partitioned uh, non-volatile storage media that you're going to use on your computer to store all your files and everything. It's not located on the ROM on the motherboard. That's where the configuration utilities are, whether it's a configuration utility for BIOS or for UEFI. And then it's also not located. Um, yeah, so it's not located in there. If that's what's in there, it's located on the storage disk. If it's BIOS, then it's in the first 440 bytes. If it's megabytes, if it's UEFI, then uh, it's located in the the EFI system partition, which can be like anywhere. It's like more flexible where it can be, but it's I think it's fewer bytes. I think it's 100 instead of 440. I don't know. All right, so let's move on to the next question. And I kind of want to see if I can use a plugin. Is there like a tutor plugin or something like that? Because that was alarming that it got that wrong. Um, I think I'm going to use prompt perfect. Um, Now this is to use databases. I don't think that's going to be useful. This is scientific research, which might be useful in this case. Um, Now this is good. This is good. I'm going to use link reader. I'm going to use show me diagrams, and then I'm going to use uh, prompt perfect. Okay, and then my prompts will be quite a bit different now. It's going to be perfect, which tells it to use prompt perfect. I'm going to say use the information at this link. Okay, and I probably can't include the highlighted stuff. And other information as is appropriate to be accurate and complete, to act as my LPIC-1 tutor and teach me and to use the Socratic method to teach me the answer to the following question. Okay, and before I hit enter, I will read the question. UEFI firmware supports extended features provided by external programs called EFI applications. These applications, however, have their own special location. Where on the system would the EFI applications be located? And I know the answer to this in the EFI system partition, which is on a formatted and partitioned uh, non-volatile storage disk, be it mechanical or solid state, that you have set up in advance on the drive that you're using to store all your files and everything. Or it could be like on its own drive. It can be like on a thumb drive. Um, it can be. It doesn't have to be in the primary disk that you're using to store your information as you'll be using your computer. It can be on like a disk dedicated to booting, something like that. And that's actually I remember from when I was in school. I learned about all this stuff like 8 years ago, and it's actually recommended that you just whatever is fastest. So like even a small flash disk, if you use the fastest possible form of storage media uh, to have your EFI system partition or your MBR located, um, your boot up process is gonna happen a lot faster. So like if you're using mechanical drives, you can get a lot better performance by like even just having like a thumb drive or some like flash media serve as your um, EFI system partition. Okay, so let's see the answer to that. See how close I was. So EFI applications are stored in the EFI system partition. Perfect. Located at any storage block with a compatible file system. Perfect. And usually FAT32, but it can be whatever you need. In my case, I'm using NTFS. And let's go above and beyond, and let's pull up my home lab and take a look at the differences between how my home lab is configured and how this like gaming tower PC is configured. And not only and then that's exciting too because now we've got to use Linux commands to figure this out. We can't, so we have to do it in a different way, in a way that's more relevant to what we're learning here. So I'm going to use Chat GPT 3.5 for this because I don't want to waste my questions. And I'm going to say, what command do I use in Linux? I'll say Ubuntu Linux to check my uh, hard drive partitions to identify the ESI. No, the ESP, the ESP. So it's the EFI system partition. Locate the EFI system partition. Okay,
To check your hard
so
drive partitions and locate the FE system partition in Ubuntu Linux, you can use the lsblk command or the fdisk command. Here's how you can do it. Using the lsblk command, open a terminal in Ubuntu. Type the following command and press enter. Copy Codel's block. This command lists all the block devices and their partitions. Look for the partition labeled as FE system partition or having the file system type VFAD, FAT32. The FE system partition is typically small, around 100 to 500 megabytes, is usually mounted at boot, FE or boot. Using the fdisk command, open a terminal in Ubuntu. Type the following command and press enter. Copy code as sudo fdisk. This command lists the disk partitions on your system. Look for a partition with the FE system or FE partition type. It may have the file system type FE system or FAT32. Note down the device name E, G, dev, SDA1 for the FE system partition. Remember to use sudo before the command if you don't have administrative privileges. Both of these commands should help you identify the FE system partition on your hard drive in Ubuntu Linux.
okay, so LSBL. Ah, look at this. Look at how nice this is. So we've got my. We know this. Uh, we know about this syntax here from the lessons. SD stands for SCSI disk, but it's used to refer to any disk that's on there, even like a USB thumb drive will be SD, and that's contrary to yeah, we see SR is another sort of disk that is a different syntax used to refer to a different type of disk, and in this case we see this is the burned in ROM. It actually shows up there, which is nice. We don't see it here in our Windows, which is annoying, which is really annoying. Unless this is it. I feel like this might be it, but even so, like it doesn't change what's down there, and it's just confusing and annoying. And then like, what's this here? Like, it could be the case that these are all different drives, but like, then what is this? I don't think that's the case. So I think this, it says partition one, so I think this is just the first partition on this disk, and then the read-only memory on the motherboard that is used for the BIOS or UEFI configuration utilities is just not listed on here, which is why so many really technically minded people prefer Linux, because you don't, it's not designed to hold your hand and coddle you and just get you far enough so that you can boot up The Witcher 3. It's designed to actually do sophisticated computer applications more than just playing solitaire on your computer. So like, yeah, it lists the ROM right there. All right, and then here's all my partitions. There we go. This is the EFI boot partition. Now there's another boot partition, which is kind of interesting. Um, I wonder if that's grub. Let's take a look at the files there. Yeah, so there's grub is located there. EFI. Let's take a look at what's in EFI. Oops. Okay, we'll go further into that. Okay, so got a bunch of things. Let's do like a tree, which I think I installed on there. Oh no, I didn't. Shoot. Okay. All right, but moving on. Let's see how far down uh, off the path of correct, non-insane information uh, ChatGPT will give us. Because we don't need an AI to do that. We can just make up our own things. The purpose of the AI is to get correct information.
Based on
That's
the
a
information from the link you provided, FE applications are typically stored in the FE system partition, ESP. This partition is a dedicated partition on a data storage device that is used by computers adhering to the Unified Extensible Firmware Interface, UEFI. The ESP contains the bootloaders or kernel images for all installed operating systems, which are stored in directories specific to each OS, device driver files for hardware devices, system utility programs, and other data such as UEFI variables. Now, let's delve deeper into this topic. Can you tell me why it's important for FE applications to have their own special location in the system?
Okay. Well, I mean, it just gave me the answer right away, which is like not what I was looking for, but it's asking me follow up questions, which is nice. One thing to note is now this other device here is a blade server, so LSBLK. It's still using EFI, and these are all mechanical drives. It doesn't have a solid state drive like I believe my gaming PC does. So you don't need, it just depends on the architecture of your like motherboard or your system. Like it's not about what kind of drives you have. Um, Mostly, it's probably about how old is your system. Most modern systems probably use UEFI as the configuration utility, and then use EFI system partitions to store all of the boot information. I'm gonna take a look at now that I've got the tree command installed. I want to run that command. Okay, so now we've got. We should have the kernel somewhere. Not sure where that would be. It'd probably be in there. Let me do a tree on that whole thing. I don't see anything. Yeah, there's just a lot of files in there too. So, oh, this is everything in Grub. This is what we saw before the EFI partition. The EFI partition looks like it's actually pretty small, or you know, it looks like there's not a lot of files in there. The Grub partition looks like it's got all kinds of files in there. And one thing we can do too that's like really exciting that I need to do more is go to uh, uh, Linux GitHub and look at the here we go, the Linux kernel uh, source tree is all online. Uh, Linus himself is still working on this every day. He did a last commit 17 hours ago. So like this is exciting. This isn't about, reading about ancient Greek literature or the founding fathers, This is stuff that will persist throughout time in a much in as or more significant of a way than like things like the Rosetta Stone or like these really important things. Like, this is that in a way, but it's here and now, and the people who are working on it are still alive. Like Linus Torvalds is throughout history, for the next 1,000 years, probably going to, you know, like his this work, this really matters, especially depending on what happens with AI. Okay. Okay, so why is it important for EFI applications to have their own special location? Uh, so that the location can be easily identified by UEFI so that the bootloader files can be detected.
That's correct. The FE system partition, especially, is a specially designated partition where the UEFI firmware knows to look for bootloader files and FE applications. This standardization allows the UEFI firmware to easily identify, access, and execute the necessary files to boot the system or run certain utilities, regardless of the operating system or hardware configuration. This is a key aspect of the UEFI's ability to provide a consistent interface between the operating system and the firmware. Now, let's consider another question. What might be some of the advantages of using FE applications compared to traditional BIOS-based booting methods?
Yeah, so the advantage of EFI applications over traditional BIOS based booting methods is that there is more flexibility in the location of the EFI, the ESP. It can be set up anywhere as a partition anywhere on any disk, but the BIOS MBR has to be the first partition on a uh, mechanical or solid state drive, and there's less flexibility of the type of drive that is compatible. This is why for ARM devices such as the Raspberry Pi, BIOS isn't possible to use.
Absolutely correct. UEFI, with its FE applications, offers a number of advantages over the traditional BIOS system. Flexibility. As you mentioned, the FE system partition, especially, can be located anywhere on any disk. This is in contrast to the BIOS system, where the master boot record, MBR, must be the first sector on the disk. Compatibility. UEFI is compatible with a wider range of devices and architectures, including ARM devices like the Raspberry Pi. BIOS, on the other hand, is primarily designed for IBM PC-compatible systems and may not work with other types of devices. GPT support. UEFI is compatible with the GUID partition table, GPT, which supports larger disk sizes and more partitions than the MBR system used by BIOS.
Oh, I
Secure
forgot
boot.
about that. That's a big
UEFI
one
also
too.
supports Secure Boot, a feature that helps protect the system against bootkit attacks by only allowing software signed by a trusted entity to run a boot. Fast boot. Some implementations of UEFI firmware provide a feature called fast boot, which can help the system start up faster than traditional BIOS. Now, let's move on to another question. Can you explain how UEFI uses the FE system partition to boot the system?
So yes, the EFI system partition is set up in advance by either the computer manufacturer or a system administrator. Uh, UEFI uses the EFI system partition to boot the system by accessing bootloader files on the stored within the ESP. Um, and we can see that uh, here. So it launches grub. Yeah. Let's take a look at the configuration for grub. So we've got to go to boot EFI Ubuntu. Okay, so we can see it's looking for. Uh, so let's do echo root. Oh, okay. Well, I'm not sure what's going on there. I mean, the root is probably like like boot because it's in that partition. So like that partition is so. Let's take a look at that. That's CFG. Oh wait, no, this is okay. I'm confused here, but it's kind of getting too far into the weeds. Let's focus on answering the next question. So yep, this is my answer. The EFI system partition is set up in advance by either the computer manufacturer or a system administrator. UEFI uses the EFI system partition to boot the system by accessing bootloader files stored within the ESP.
That's correct. The UEFI firmware knows to look in the FE system partition, especially for bootloader files. Here's a more detailed breakdown of the process. ESP setup. The FE system partition is typically set up during the installation of the operating system or by the computer manufacturer. It's formatted with a file system that the UEFI firmware can understand, usually FAT32. Storing bootloaders. The ESP contains the bootloaders for all installed operating systems. These are usually stored in a directory named after the vendor or operating system in the root of the ESP, e.g. FE, boot, or FE, Microsoft. UEFI Boot Manager. The UEFI firmware includes a boot manager, which is a program that can read the ESP and identify valid FE applications, including bootloaders. The boot manager can present these to the user as boot options. Boot process. When the system is powered on, the UEFI firmware loads the boot manager, which reads the ESP and launches the default bootloader, or offers a choice to the user if multiple are available. The bootloader then loads the operating system into memory and transfers control to it. This process allows for a standardized, flexible, and extensible boot process that can support multiple operating systems and advanced features like secure boot. Now, let's consider another question. What are some of the challenges or potential issues that might arise when working with UEFI and FE applications?
Okay, so let me read that one more time because I was distracted there. So the UEFI firmware knows to look in the UEFI system partition. Um, that or also known as the EFI. So the EFI system partition for bootloader files. Here's a more detailed breakdown of the process. Step 1, ESP setup. The EFI system partition is typically set up during the installation of the operating system or by the computer manufacturer. It is formatted within a file system that the UEFI firmware can understand, usually FAT32. In this case, it's different. It's Linux file system. I'm not sure what that is exactly. And then on my Windows, it's NTFS. Storing bootloaders. The ESP contains the bootloaders for all installed operating systems. These are usually stored in a directory named after the vendor or operating system in the root of the system. Okay, so we saw that. Mine was Linux. So let's do tree boot and then EFI. So now we're looking at the EFI, the EFI system partition. And yep, we've got it for the operating system. And here we've got, looks like we've got multiple bootloaders, grub, mmx, and shimx. Okay, next is the UEFI boot manager. The UEFI firmware includes a boot manager, which is a program that can read the ESP and identify valid EFI applications, including bootloaders. The boot manager can present these to the user as boot options. All right, then the boot process. When the system is powered on, the UEFI firmware loads the boot manager, which reads the ESP and launches the default bootloader, or offers a choice to the user if multiple are available. The bootloader then loads the operating system into memory and transfers control to it. This process allows for a standardized, flexible, and extensible boot process that can support multiple operating systems and advanced features like secure boot. Now let's consider another question. What are some challenges or potential issues that might arise when working with UEFI or and EFI applications? Okay, so one challenge would be that the EFI system partition was not correctly set up. Either the partition is missing or the file system used is not compatible. A challenge with UEFI could be that the settings are misconfigured.
Indeed, those are some of the potential challenges when working with UEFI and FE applications. Incorrect ESP setup. If the FE system partition, especially, is not set up correctly, the UEFI firmware may not be able to find or launch the bootloader. This can happen if the ESP is missing, if it's not formatted with a compatible file system, usually FAT32, or if the bootloader files are not in the correct location. Misconfigured UEFI settings. UEFI firmware typically includes a setup utility that can be accessed during the boot process. This utility allows users to configure various settings, such as the boot order, whether secure boot is enabled, and so on. If these settings are misconfigured, it could prevent the system from booting correctly. For example, if secure boot is enabled but the bootloader is not signed with a key that the firmware trusts, the firmware will refuse to launch the bootloader. Compatibility issues. While UEFI is designed to be a standard interface, not all implementations are the same. Some systems may have UEFI firmware that behaves differently than expected, or that is not fully compatible with certain operating systems or hardware. Software issues. Some operating systems or applications may not fully support UEFI or may have bugs that cause issues when booting via UEFI. This is less common with modern software but can still occur, particularly with less commonly used operating systems or older versions of software. Understanding these potential challenges can help in troubleshooting any issues that arise when setting up a UEFI-based system or installing a new operating system. Now, let's consider another question. How can these potential issues be mitigated or resolved?
Yeah, so verify the UEFI settings by hitting F2 or ESC during boot to take you into the UEFI configuration utility menu. Verify the UEFI partition by accessing the disk in another system that already has the operating system loaded and using the tools within the OS to verify the disk partitions and file systems.
Absolutely. Here are some steps to mitigate or resolve potential issues with UEFI and FE applications. Check UEFI settings. As we mentioned, you can access the UEFI firmware settings by pressing a specific key, often F2, F10, F12, ESC, or DEL, depending on the system, during the boot process. In the firmware settings, you can check and adjust settings like the boot order, secure boot, and others. Verify the especially. If you suspect an issue with the FE system partition, you can check it by booting from a different operating system or a live system, like Live Linux USB. Tools like fdisk, lsblk, or gpart on Linux can show you the partitions on the disk, and you can mount the especially to check its contents. Update firmware. If you're experiencing compatibility issues or unexpected behavior, it may be worth checking if there's a firmware update available for your system. Firmware updates can often resolve compatibility issues and add support for new features. Use compatible software. Make sure to use an operating system and applications that support UEFI. Most modern operating systems, including Windows 10 and recent versions of Linux, fully support UEFI. Seek help. If you're still having trouble, don't hesitate to seek help. There are many online communities, forums, and resources where you can ask questions and get help with troubleshooting. Remember, working with UEFI and FE applications can be complex, but with careful troubleshooting and the right resources, you can resolve most issues that come up. Now, let's consider another question. Can you explain how secure boot works in the context of UEFI and FE applications?
Yeah, so that's another good example. If your read-only memory contains a BIOS, and then instead of an MBR, you have a EFI system partition on your disk, that's obviously not going to work. Okay, so yes, secure boot works in the context of and EFI applications by, and I remember it talked about it later, so I'm going to go back to what it said about that and enter that in for my answer. Okay, by only allowing software signed by a trusted entity to run at boot. Let's see if we can identify like a file that would do that. So this is secure boot. Here's a, I'm not sure what would do that. Let's see. Gonna change directory. Let's see what these EFI look like. Yeah, those are compiled files. Yeah, I don't know what that looks like, but this is the answer.
That's correct. Secure boot is a feature of UEFI that helps to prevent unauthorized code from running during the boot process. Here's a more detailed explanation. Signature verification. When secure boot is enabled, the UEFI firmware checks the digital signature of any FE application, including bootloaders, it tries to run. The firmware has a list of trusted signing keys stored in its NDRAM. Trusted keys. If the FE application signature can be verified with one of the trusted keys, the firmware allows it to run. These trusted keys are typically installed by the manufacturer and include keys for major operating system vendors. Revocation lists. The firmware also has a list of revoked keys, known as a DVX. If an EFI application's signature matches a key in this list, it is not allowed to run, even if the key is also in the list of trusted keys. This mechanism allows for keys to be revoked if they are found to be compromised. User control. In many systems, the user can add their own trusted keys or remove existing keys, allowing them to control what software can be run during the boot process. Secure boot helps to protect the boot process from bootkits and other types of malware that try to insert themselves into the boot process. However, it also means that any software that runs at boot, including operating systems and their bootloaders, must be signed with a trusted key. Now, let's consider another question. What are some potential challenges or limitations of using secure boot?
Alright, I will deal with that follow-up question in just a minute. I gotta take a break. I'll be right back. Alright, I'm back. Still feeling good, I think. So okay, I can replay this. So I'm gonna uh actually no, I played that already. So I'm gonna go next to the next one. What are some potential challenges or limitations of using secure boot? So secure boot can add an extra layer of inconvenience and delay or disrupt safe and secure contact with the system, necessarily, especially if advanced and unconventional research and development work is meant to be conducted.
Indeed, while secure boot provides an important layer of security, it can also introduce some challenges and limitations. Compatibility issues. Not all operating systems and bootloaders support secure boot or are signed with a key that the firmware trusts. This is particularly an issue with some Linux distributions and other less common operating systems. Development and testing. If you're developing your own operating system or bootloader, or if you want to use a bootloader that isn't signed by a trusted key, you'll need to either disable secure boot or go through the process of signing your software and adding your own key to the firmware's list of trusted keys. Hardware restrictions. Some systems may not allow you to disable secure boot or manage the list of trusted keys, which can limit your ability to use certain software or operating systems. Malware risks. While secure boot helps protect against bootkits and other types of malware, it's not a complete solution. For example, it doesn't protect against malware that infects the operating system after boot. Despite these challenges, secure boot is an important tool for securing the boot process and preventing unauthorized code from running a boot. It's just one part of a comprehensive approach to system security. Now, let's consider another question. How can these potential challenges or limitations of secure boot be mitigated or managed?
Okay, so they can be having a system administrator having a system administrator manage the system who has a professional skill set to identify and resolve issues with the issues mentioned.
Absolutely. A skilled system administrator can effectively manage and mitigate potential challenges or limitations of secure boot. Here are some strategies they might employ. Understanding secure boot. The first step to managing secure boot is understanding how it works and what it does. This includes understanding the boot process, digital signatures, and how the firmware verifies
Do
these
I
signatures.
have secure boot?
Managing keys. In many systems, the user or administrator can manage the list of trusted keys. This can include adding new keys, for example, if you want to use a custom bootloader or operating system that isn't signed by a key the firmware trusts, or removing keys. Disabling secure boot. If necessary, secure boot can often be disabled. This can be useful for certain types of development or testing, or for running an operating system that doesn't support secure boot. However, it's important to understand the security implications of doing so. Staying updated. Keeping the system's firmware and operating system updated can help ensure compatibility with secure boot and protect against security vulnerabilities. Seeking help. If the administrator encounters issues they can't resolve, they can seek help from others. This can include reaching out to the system or motherboard manufacturer, asking for help in online communities or forums, or consulting with other IT professionals. Remember, while secure boot can present some challenges, it's a valuable tool for securing the boot process and protecting against certain types of malware. Now, let's consider another question. Can you explain how UEFI interacts with the operating system once the system has booted?
Once the system has booted? Oh, not really. No.
That's perfectly fine. Here's a brief explanation. Once the system has booted, the role of UEFI is largely done. Its main job is to load and start the operating system. However, UEFI firmware does provide runtime services that the operating system can use even after the system has booted. These services include time services. The operating system can use UEFI runtime services to get or set the system time and date. Variable services. UEFI variables are used to store information that needs to persist between boots. The operating system can use UEFI runtime services to read and write these variables. Reset services. The operating system can use UEFI runtime services to reset the system. Boot services. These are services related to the boot process, such as loading files into memory and starting other FE applications. However, these services are typically not available after the operating system has booted. It's important to note that the interaction between UEFI and the operating system can vary depending on the specific firmware implementation in the operating system. Now, let's consider another question. Can you explain the difference between UEFI and BIOS?
Okay, so these like run level messages must be stored in the UEFI. Let me try to look at those messages again. This is kind of taking me away from the goal of this video, which is to complete all of the exercises, but think I'm only going to be able to get these exercises done. But let's take a look at these boot messages. So yeah, um, so like let's take a look at this command here, journals ctl list boots. Let's take a look at the journal ctl boot -4. So this must be stored in the UEFI because that's how it persists between boots. So that's interesting. Um, so I'm kind of away from this right now. Um, so let's look at the other. Let's look at another question. So I've got my. Yep, I've got my. Okay. So okay, so let's go to the other question. Okay, so we're going to say perfect to use the plugin. Then we're going to say use the information at the following link, and then plug in the learning materials here. And other information as is necessary and relevant and accurate to use the Socratic method to teach me the answer to this question. Okay, so we finished this one. UEFI firmware supports extended features provided by external programs called EFI applications. These applications, however, have their own special location. Where on the system would the EFI applications be located? This is an easy one. Kind of overcomplicated it talking to GPTs for so long. It's in the EFI system partition, which can be on any disk. It can even be on uh, special architectures, ARM architectures on like Raspberry Pis. Um, so um, it's located on that disk, and then the UEFI um, configuration utility has a target to where it is. All right, so next question. And I will read the question. Oh, should we answer the following question and then say use diagrams whenever necessary. All right, the question is bootloaders allow the passing of custom kernel parameters before loading it. Suppose the system is unable to boot due to a misinformed root file system location. How would the correct root file system located at /dev/dba3 be given as a parameter to the kernel? And this takes quite a bit longer because it's got to reach out to the link.
Based on the information from the link, let's explore the solution to your question using the Socratic method. Understanding the problem. The system is unable to boot due to a misinformed root file system location. We need to pass the correct root file system location to the kernel. The correct location is dev SDA3. Do you understand the problem we're trying to solve? Understanding bootloaders. Bootloaders are programs that load the operating system into the computer's memory when the computer is powered on. They also allow passing of custom kernel parameters before loading the kernel. Can you explain what a bootloader is in your own words? Understanding kernel parameters. Kernel parameters are used to provide the kernel with information about hardware parameters that the kernel wouldn't be able to determine on its own or to override certain default kernel settings. In this case, we need to pass the correct root file system location as a kernel parameter. Can you explain what kernel parameters are and why they are important? Solution. To pass the correct root file system location as a kernel parameter, you would typically need to edit the bootloader configuration file. In the case of grub, the most commonly used bootloader on Linux, you would add the following line to the etc. default grub file. Makefile copycode grub underscore cmd line underscore linux underscore default equals quiet splash root equals dev sda3. Then you would update grub with the following command. SQL copycode sudo update grub. This would pass dev sda3 as the root file system location to the kernel. Can you explain the steps you would take to solve this problem? Understanding the solution. The solution involves modifying the bootloader configuration to pass the correct root file system location as a kernel parameter. This allows the kernel to know where the root file system is located, enabling the system to boot correctly. Can you explain why this solution works? Now, let's visualize this process with a diagram. Here is a sequence diagram that visualizes the process. You can view this diagram in a new tab. Here is a sequence diagram that visualizes the process. You can view this diagram in a new tab. You can edit this diagram online if you want to make any changes. Here is a sequence diagram that visualizes the process. You can view this diagram in a new tab. You can edit this diagram online if you want to make any changes. The type of the diagram is a sequence diagram in Mermaid language. To view ideas for improving the diagram, use the key phrase show ideas. To view other types of diagram and languages, use the key phrase explore diagrams.
Okay, so user powers on the computer, then the bootloader loads the kernel in the memory, um, passes the kernel the parameters, um, and then it uses the passed parameters to, yeah, and the parameters are the EFI partition. Is that maybe the next? Is that what this is? Um, hmm. Okay. All right. That's confusing. It's just like not doing it as good as it was before I was using these plugins. But I think the answer isn't that tricky. So bootloaders allow the passing of custom kernel parameters before loading it. Suppose the system is unable to boot due to a misinformed root file system location. How would the correct root file system located at /dev /SDA3 be given as a parameter to the kernel? And the answer to that is it's configured somewhere. I forget. Um, so from the grub menu, it is possible to choose which one of the installed kernels should be located and to pass new parameters to it. So you pass a parameter to it from the grub menu. That's the answer. And the parameter you would pass to it would be the root parameter, which sets the root partition. Um, but this is interesting because oh yeah, SDA3. So yeah, you set the oh SDA3 in my case. I mean, it's going to be different depending on which system. So how do let me see if I can check the okay. So what command can I use in Linux to check the uh, kernel parameters?
In Linux, you can use the
Proc.
proc file system to check the kernel parameters. Specifically, you can use the cat command to view the contents of the proc cmd line file, which contains the kernel command line parameters. Open a terminal and run the following command. This will display the kernel parameters that were passed during the system's boot process. Each parameter is typically separated by a space. Additionally, you can use the syscdl command to check and modify kernel parameters. However, the syscdl command primarily deals with runtime parameters and not the parameters passed during boot.
Oh, that's a good point. So here it is, but these are runtime parameters, so it's not like when the system is booting up, it won't draw it from here. It'll draw it from the grub menu, so it might be different than what I see here. Okay. So let's take a look at the answer to this one. So uh, the answer is the root kernel parameter should be used in the grub menu. Okay. Yeah, I'm just kind of overcomplicating things with using ChatGPT. Let's go back to using it without plugins. So just the default, and then we'll use the same. So we'll say act as my LPIC-1 tutor, use the Socratic method to teach me the answer to this question. So the question is the boot process of a Linux image ends up with the following message. Alert does not exist, drop into a shell. What is the most likely cause of this problem? And this one I know already, that partition doesn't exist. or the disk doesn't exist.
Sure, let's start by examining what you understand from the message. Based on your current knowledge, what does dev SDA3 signify in the context of the Linux system?
It signifies a uh, hard disk. Uh, in this case, the first hard disk, disk A, and on that disk, it signifies the third partition on that disk.
That's correct. Now, considering the alert message states dev SDA3 does not exist, what could be some potential reasons for the system not being able to find this partition?
One, the partition doesn't exist. For example, there's only partitions SD1 and SDA2, but not SDA3. 2, that disk does not exist. For example, the disk was never slotted into the SCSI or SATA port 3. The disk isn't formatted correctly. Okay, we'll stop there.
Excellent points. You've covered some of the key possibilities. Let's also consider a few more scenarios. What might happen if the bootloader was incorrectly configured or if the file system of dev SDA3 is corrupted? What effect might these situations have?
Okay, so if the bootloader was correctly configured, it might not be looking for the files in a valid location. If dev CA3 is corrupted, although the bootloader might be finding the correct files, they might not be in a usable condition.
Correct. A misconfigured bootloader might be incorrectly pointing to dev SDA3 when the actual root partition is elsewhere. Similarly, even if dev SDA3 is the correct partition, a corrupted file system could prevent the system from reading it correctly, leading to the system saying that the partition does not exist. Given these considerations, if you were faced with this problem in a real-life scenario, what steps would you take to troubleshoot and resolve this issue?
Yeah, so I would reboot the system, pressing del C F2, whatever button is necessary to go into the UEFI BIOS configuration utility. From there, wait, I don't know how to get to the grub. Would get to the bootloader menu somehow. How do I do this? I don't know. And from there, I would check and possibly reconfigure the kernel parameters if the kernel parameters are correct, I would pull out the disk or use a utility to verify the partition setup on the disk. It's got to think hard about that one.
Good. Initial troubleshooting steps. Here's how you can fill in the gap. From the BIOS UEFI setup, you would want to set the boot priority to boot from live Linux USB or CD if available. Once booted from live environment, you can use command line utilities like fdisk, lsblk, or blkid to verify the disk and partition setup. For example, using fdiskl will list all the disk partitions and you can check if dev sda3 actually exists or not. If dev sda3 exists and is the correct root partition, you can check the file system integrity using fsck file system check. Be careful, though, as this can potentially result in data loss if the file system is severely corrupted. If the problem seems to be with the bootloader, say, grub configuration, you would want to inspect the relevant configuration files. The primary one is usually boot grub grub. CFG. You're looking to ensure that the root parameter in the grub configuration points to the correct partition. Does this clarify the steps you need to take? Great. Remember, Linux system administration, including troubleshooting boot issues, can be complex and may require a combination of knowledge, experience, and sometimes a bit of creative problem solving. It's good to know the fundamentals, as you clearly do, and build on them with hands-on practice and deeper learning. If you have any other questions or need further explanation, feel free to ask. Good luck with your LPIC-1 certification preparation.
So the one thing though is like, so they want you to check this, but like you can't check it. You can't check. You have to check it using the live Linux USB or CD. Like you can't check it after the system is booted.
Yes, you're correct. If you're not able to boot into your system due to the error message you described earlier, you won't be able to check boot grub grub.
Right.
CFG directly from that system. Instead, you would need to boot from a live Linux USB or CD, as you suggested, and then mount the file system of the problematic system on a directory in your live environment. Once you have done that, you can navigate to the mount point, go to the boot grub directory, and then view the grub CFG file. So, for example, if you mounted the root file system of the problematic system on a directory named mnt, you could then check the file by looking at mnt boot grub grub CFG. Remember to be very careful when editing bootloader configuration files, as incorrect settings can prevent the system from booting correctly. Always make a backup of any configuration file before you start making changes.
Okay, so the answer to that is, um, yeah, it's just not. There's something wrong with this partition. The partition doesn't exist. Yeah, it's yeah. Okay, so that's it to the guided exercises. Wish I could have made more progress than that, but I had about an hour and 20 minutes, so I need to stop here. So thanks for watching, and stay tuned for the explorational exercises, the summary, the answers, which we already kind of went through, and then the next lesson 101.3.